All right, so we're going to be shifting this week away from our the stuff we were doing last week. I think we're on to new stuff. Yeah. Um, and we're going to be talking more about arcs and placement. Um, it's a little bit odd, not hard, just a little bit different. So let's start with 6.6, the warm-up. We're going to be using the degree measures of the central angle to find the length of arcs. So I believe you did this in Math 2 Accelerated. I'm not sure when, but it is should be familiar. So what we're going to do is it says to set up a proportion. And so that means we need two fractions that are equal to one another. So our first fraction will be the central angle over the whole circle, and that's equal to what we're trying to find, the piece, the arc length, over the circumference of the circle. So since this circle has a radius of 10 inches, our circumference is 20 pi. And so basically, this is our proportion that we set up. It's always the central angle over the whole circle, and that's equal to the arc length divided by the circumference. So, pretty straightforward. This is 1/3. 120 divided by 360 is 1/3, and that's equal to x over 20 pi. We cross multiply, and we get 20 pi is equal to 3x, and so x is equal to 20 pi divided by 3. So that's how you do that. Go ahead and pause the video now and do question number 2 and question number 3. Question 3 is a little different. Question 2 is the same. Like I said, 2 is exactly the same. We end up with 315 over 360, which is 7/8. We cross multiply, and then end up with 7 times 32 pi divided by 8, which is 28 pi centimeters. For question 3, the circumference of circle A is 40 meters. The circumference of circle B is 80 meters, which means we took the circumference of circle A and doubled it to get the circumference of circle B. The relationship between the radiuses is the same. It's twice. We have whatever the radius of circle A is times 2 will be the radius of circle B, because there's no unit changing from meters to, it's just meters versus meters, and so they're exactly the same. All right, so next we have what we're talking about today. So Alice, Javier, and Veronica are responsible for preparing a recently discovered archaeological site. The people who inhabited the site built their city around a central tower, and the first job is to figure out where they should mark stakes so that they can keep track of where they're discovering things on the site. So when you do an archaeological dig, you have to basically lay everything out so that you can figure out, so what was the relationship in the city. What they know is there's the central tower in the middle that's sticking out of the ground. Basically, they already found it. It's where they found the ancient habitations, and so they're trying to figure everything else out. So Alice has suggested that they place stakes in a circle around the tower where the distance to the marker is the same as the radius. They like that idea, but Javier's worried that they're going to need different markers for each circle, for how, as far as they go from the circles around the central tower. Do we agree or disagree? So we have our central tower, and then we have the marks and another circle out here and so on, kind of like a target sign. And Alice's idea is that we use the radius as our unit of measure, and we go around each circle using the radius as the unit of measure. And granted, my outside circle is a terrible circle, but ignore that part. So, which means that the distance, the arc length is going to change every time, because the arc length is always going to be equal to the radius of the circle. And Javier's, what he's specifically said he's concerned about is the number of markers needed. He's saying that they're going to need additional markers if the circle is bigger, if the radius is bigger. And do you agree or disagree? So go ahead and have a discussion with your group about that, whether we agree or disagree, and pause the video and I'll come back and explain my decision on that. So, in my opinion, you actually don't need any different size circles. If you think about it, it's always going to be the same because the circle, which is and the arc lengths are related to the radius. So the arc length, if from the warm-up we just discovered, is always the central angle divided by 360, which is equal to the arc length divided by the circumference. And the circumference of every single circle is 2 pi r. So every circle has 2r times pi going around it. So 2 pi times r, or in other words, we're going to have the exact same amount of marks because r is going to change with when the circles get bigger or smaller, and we'll have the same amount of marks, which will always be 2 pi. So that's around 6 and a little bit marks around the circle. So here's a better picture than the one I drew. Show where the stakes are going to be using Alice's method. And so what you're going to want to do here is use something flexible. Girls, if you have a rubber band for pulling back your hair in your pocket, that's perfect because it's sturdy enough that it'll hold its shape. And then you can use it to measure your radius, like, pulling it and measure your radius and then marking off your tower so within radius units. Something like this and that's done terribly, so there should be a total of 6 marks. 1, 2, 3, 4, 5, actually 7 marks, 6 and then 1 more. So I didn't quite do a good job here, but that's the idea, is you're going to have those marks. So if you have a rubber band or a piece of string or shoelace, if you wanted to untie your shoes to do this, which would be silly, or if you have earbuds and you could use the cord, not wireless ones, of course, won't work, but something that you could use to mark that off. Go ahead and see what you can come up with and mark them off. So your final answer should look something like this. So each of your marks being 12 meters apart, and that's 24 times pi. 24 times pi. Which is around 75, and 75 divided by 12 is around 6.28. So there should be a total of 6. 1, 2, 3, 4, 5, 6. And so I'm off because that should be, I messed up, which I knew I was doing because there should be basically 7 total dots on the circle. But the idea here is basically similar, where you'd have them be out. I'm missing a dot probably in here somewhere. These last 3 dots are a little too close, spread apart. But that's the idea. It's actually really hard to do. If you recall last year in Math 2, you started talking about radians and radian units, and that's where we're leading here, is into that measurement. So in part 2, after looking at their model, this is not enough. We're not really getting enough information here. So Veronica says that they need more stakes if they intend to be specific with the location of the artifacts. They want to basically create a grid to mark off sections. They're going to evenly space 12 stakes around each circle using the coordinate grid to label points. They want to make sure they record the distance around the circle at each stake. The central tower is located at the origin, and the first 12 stakes for the inner outer circles are placed at 0, 12 and 12, 0 and 18, 0 respectively. So like this, they're basically here on this. And so the rest of our task today will be to plot all of these points on the stake and write down their ordered pairs. And so we're going to break it into 12 sections. I'm going to give you some of the easy ones right here and here, right? We're going to have them on the axes. Those are the easy ones. And so that's 4 sections. And then we need to break each of these into 3 more sections, 3 sections in each quadrant to bring our total to 12. And so, something like here and here. 3 sections, which means 2 more dots. 3 sections or 2 dots. And your job is to figure out where they all go and how to figure out what the ordered pairs are. You're going to keep good track of this. It's going to take a while. So you're going to want to pause the video and spend the time working together, figuring out where they are, what the ordered pairs are, how do you find them. Basically what's going to happen here, another hint, is we've got 30 degrees in each of these sections because we took 90 and broke it into 3 sections to create these 2 more dots we have to find. And we're gonna kind of use sine and cosine to help us figure this out, and that arc length bit to figure out where everything is. Remember, sine is the y movement and cosine is the x movement, and see if that helps you. Go ahead and pause the video now, see what you can come up with. Okay, so I'm going to give you a couple of hints on the first circle only, just to help you along if you're stuck. And so here are the calculations I did for 4 of the points. 2 in the first quadrant and 2 in the fourth quadrant. So on this one, I didn't actually write how I got 6. What I know is that I'm going to be dealing with 30 degrees for my first angle and then 60 degrees for my second angle in this quadrant. And so the sine of 30 degrees is 1/2, so half of 12 is 6. And then 12 times the cosine of 30 degrees for my x term is 10.392. So I end up with 10.392 comma 6, and then 6 comma 10.392 for my other point, which is the cosine of 60 degrees, which is 1/2. So there's where 6 came from. And then 12 times the sine of 60 degrees, which turns out to be the opposite. So what happens is they switch. And so then I did the same with the full calculations down here. 12 times the cosine of 330 degrees, and 12 times the sine of 330 degrees, giving me my 2 numbers, and so on with these. So that's your hints, and use that. You basically need to figure out what angle you're at. So we're going to be 90 plus 30 here, and then 90 plus 30 plus 30 twice here, or plus 60, and so on around the circle as you go. So that will help you finish it. And again, you need to do, for both circles, all the calculations and somehow keep track. You might want to be using a piece of paper to write all these down on that you then would attach to your notebook, because there's a lot of calculations that are happening and it's really hard to put it right here on the circle. So good luck to you, and I will see you soon.